Hey everyone, this is Christian Hulteberg again, coming to you with another webinar on catalysis. So again, Hulteberg Chemistry Engineering. We're a small specialized engineering firm doing heterogeneous catalysis. We work with the full chain from research and development through production, and we can help you anywhere from idea to implementation. Today we'll talk about something that is very dear to me. We'll talk about catalyst testing. I will go through different types of reactors and when to use which reactor type. And for those of you who listened to our previous webinar a few days ago, this will be somewhat similar. Then we will go into the nitty-gritty stuff and we will talk about gradients. How can gradients in temperature and concentration influence your catalyst testing? Very important stuff. I will then give you some conclusions, and then there is a lot of things to read in this area. So there are 2 slides on further reading, and I will also provide a nomenclature because there are quite a few formulas to go through today. But let's start from the top. So zooming out, heterogeneous catalysis is really a workhorse in the chemical industry. About 90% of all the chemicals that we produce by volume involve some kind of catalyst in their production. And when you look at bulk chemicals, dedicated plants, they are almost all of them are based on heterogeneous catalysis. The amount of catalyst is somewhere between 2 million and 6 million tons per year, and it's a rather large market in its own right. So 30 billion market cap. It's what we would probably refer to as a special chemical market, and it's really, they're very present in fuels and chemicals. Of course, when we talk about catalysis, research development activities are always ongoing, and looking at doing catalyst tests to discover new catalyst materials and alter existing ones and improve them is something that is very central to catalyst research. And for doing that, you need to do catalyst testing. So catalyst testing is really important for several different reasons. First of all, you have this catalyst discovery aspect where we have one reaction that we are targeting, but the current catalysts aren't good enough, or nobody has considered this reaction before. Then we need to do something that, well, we need to find and identify a new catalyst. And what we do then is basically trial and error, or intelligent trial and error, try to find catalyst materials that are active enough, selective enough for the reactions. And once we've done that, we would like to also know things like the kinetics of the reaction. So how fast is the reaction happening on the catalyst surface? What are the limiting factors? And what is the reaction mechanism? So catalyst discovery contains a lot of these traditional research topics, but you can also do catalyst testing for other purposes, and that purpose can be for instance, catalyst diagnostics. So if you have an industrial reactor which is on stream, you can extract a small amount of catalyst to make some kind of diagnostics test. What is the performance of this catalyst? How far from being fully deactivated, for instance, is the catalyst? And finally, you can also do catalyst testing to verify the catalyst lifetime under real-like conditions. So we choose reactor depending on what we want to do with respect to testing. So if our purpose is to do catalyst discovery, so finding new catalysts for a reaction, we will most likely use a scouting reactor. Once we've found a suitable catalyst, we will move that up in size with respect to both reactor diameter and catalyst volume in what we referred to as a catalyst improvement or industrialization reactor, so catalyst optimization reactor type. Then finally, we want to do some kind of pilot testing, and that's done normally in a prototype reactor. So in a scouting reactor, we start by measuring activity. We are also interested in selectivity and other things. And in this reactor, it's really important that we try to minimize the influence of these gradients that can occur. Different temperatures in different regions, diffusion issues, things like that. And it should be really easy to exchange the catalyst because we're now in screening mode, so we have a lot of ideas on what type of catalysts we can test. We want to spend as little time not testing as possible. So having multiple reactors trying catalyst at the same time is one option, but also having multiple reactors so you can easily switch between one reactor and the other in the same setup will also improve testing time. In the scouting reactor, we are, as I said, trying to measure the parameters that are not influenced by heat and mass transfer. So we're actually interested in the intrinsic kinetics, the reaction that happens on the actual surface without limitations in moving reactants and products in and out of the catalyst or from the gas bulk to the catalyst surface. And this is highly desirable, but it might not always be possible. So if it's not possible to measure without these gradients, we will make a best estimate of how to estimate them. And for that, we use numerical models, and I will show you some equations that relates to that in a few slides. So, and then in the catalyst optimization reactor, we take these handful of commercial successful candidates that we tried in the screening, and we bring them towards commercialization. And in this stage, we definitely prepare and we test catalyst in the same form as they will be in the actual industrial reactor. We'll put them pellet form, we'll make extrudates, we'll make monoliths, and then we get closer to the industrial conditions. We're still not there, but we do definitely include gradients in the testing. And in industry, most reactions operate with gradients, so we just have to live with that. Finally, the prototype reactor. We need to do this as small as possible, but it should still be relevant. So we try to get a large enough section of a commercial type reactor without making it any larger than we have to, because the larger, the more expensive. We use this for scale up. And one of the things that we really want to look into in this case is the actual gradients and the performance with respect to pressure drop. We also want to know what happens if we remove the catalyst and put it back in again. How repeatable is the pressure drop? How repeatable is the performance? And also, are there heat or mass transfer limitations? A very good prototype would be a single tube if your final application is a multi-tube reactor, which are quite common both in strongly exothermic and strongly endothermic reactions. And then if you look at all of these reactors, they can in theory be of different types. And we won't go into what represent these reactors right here and right now. Just mention that we have non-stationary reactors where inlet concentration and conditions change. They can be batch, they can be semi-batch or fed batch reactors, or indeed transient reactors when you're intendedly or purposely changing the conditions. Or they can be stationary, which we also call continuous or continuous flow reactors, like plug flow reactors, which is the most common in testing. We have fluidized bed reactors, and then we have continuously stirred tank reactors. And we can break it down into this scheme here where we have non-stationary to the left. Again, we have the batch, we have the semi-batch or fed batch, we have the transient reactors. For the stationary, again, continuous stirred tank reactor, fluidized bed, and plug flow reactor. But the plug flow reactor, as opposed to the other two, can actually be broken down into even more categories. So we differentiate, for instance, between integral and differential. In integral testing, we're actually doing quite a lot of change. So if you compare inlet and outlet, it's a large change in, for instance, concentration. So the conversion is high. We might range from 0 to 100% conversion over the reactor bed. So we try and we test over the entire catalyst reactor or the activity span at once. And that may give us very good information, but in different areas of the catalyst bed, you might have different kinetic expressions representing your reaction. So when you go from a high concentration to a low concentration of a starting product, you might actually see a change in reaction regime. We can further investigate those regimes by going to differential type testing. In differential testing, we're doing very little conversion, definitely below 10%, maybe as low as 2 to 3 to 5% conversion. And the idea here is to do a little change and measure the kinetics for that band of conversion. And then you go through the entire band of conversion by mixing the gases up. And you can do this in a few different ways. Either you do single pass. Single pass is actually quite difficult because it poses a significant analytical challenge. You have very small change from the inlet versus the outlet, so the analytical work will be more challenging. Then we have the option of doing a recirculating reactor where we're taking the gas multiple times around and just extract a small part and add a new small part of fresh gas. That way we will get a larger gas volume to analyze, which makes the analytical challenge smaller. And this recirculation can be done either internal to the reactor or external to the reactor. And there are commercial systems that you can buy, or you can of course build your own. But given these different types of reactors, there is one very important question that we need to ask us, irrespective of what type of testing we're doing. And that question is, when we measure activity, what do we actually get? So we measure a reaction rate. And most likely, that reaction rate will not be exactly the reaction that happens on the surface. So we're not going to measure the intrinsic reaction rate. We do get a reaction rate, but it's influenced by many different things like transport, temperature gradients in the material, things like that. So these deviations, if you want to call it that, from perfect behavior are, to a large extent at least, traced back to these gradients. And in the following, there's mainly concerns about gas-solid and liquid-solid reactions. And we will go through and have a look at all of these gradients. And we'll start again from the macro perspective with gradients that is in the reactor. And then we'll move to things that happen around the catalyst particles, and then finally inside the catalyst particles. And if we look at these gradients that are inside the test reactor, they can be both in the direction of the flow, so in the actual direction. They can also be from the center of the reactor to the wall of the reactor, so in the radial direction. And talking about the walls, there is also what we refer to as a wall effect, where you have different properties close to the wall because you have not as good catalyst packing there as you have in the rest of the bed. And then finally, we have pressure drop over this test reactor. So we might actually have a pressure difference between the inlet and the outlet that needs to be considered. Then for the other two cases, where we move from the gas or liquid bulk to the catalyst particle in the stagnant layer around the particles, there will be temperature and concentration gradients. And that is also the case inside the particles. So these catalyst particles are porous. Inside these pores, there might be cases where you will have a higher temperature, for instance, in the center than at the surface, and that will also influence your concentration. I hope that is clear so far, and I'll just give you a very simple schematic of a reactor, and we'll use these denominations later. So we have the reactor walls here. We have catalyst particles inside the reactor, the brownish grains here. We have the diameter of the reactor, which is dt, which is the inner reactor tube diameter. We have lb, which is the bed length, and then we also have dp, which is the particle diameter. And before we go to the equations, we could just make some general statements. And first of all, for gas solid operations, there will be most severely gradients with respect to temperature in the entire bed, because the heat conductivity of inorganic oxides are quite poor, and that's normally what we have as catalysts. And also the heat conductivity of the gas is low. So if there's a possibility, if there is reaction heat generated somewhere or indeed consumed somewhere, it's likely that it's not transported somewhere else. So in the bed, the temperature gradient is believed to be the ones that has the largest influence. Then you have a temperature gradient between the particles, and that's more severe than problems with concentration gradients inside the particles. And the concentration and temperature gradients inside the particle, they go sort of hand in hand, so they're on the same level of severity. And then finally you have least problems with concentration gradients between the particles in the general case, and all this has to do with the lower heat conductivity of the gas and the low heat conductivity in the catalyst bed. In liquid operations, so if you have a liquid reactant and product and a solid catalyst, the concentration gradients are the most important. In liquids, you have much higher heat conductivity. You also have much lower diffusivity, so you have much lower movement around the molecules, well, compared to the gas phase system. So yeah, that influences that. And what we need to do when we start looking at this is, first of all, so we start on this macro level, we start looking at the test reactor, and then we want to see, first of all, what is the minimum bed length we can have when we're testing to neglect the effects of axial dispersion. And axial dispersion is basically if you have molecules in a liquid, how at a certain temperature, how do they move around spontaneously? And what we do is we calculate the Bodenstein number, and the Bodenstein number is actually the relationship between the actual dispersion, so how fast do the molecules move in the actual direction on their own, compared to the velocity we have around the catalyst particle. So U here is the linear velocity of the gas or liquid moving through the catalyst bed. So we use this relationship and we put it into this equation where we have the relationship between the bed length and the catalyst particle diameter. and this has to be larger than this expression, which is empirical to some extent, and it's 20 times the reaction order. So if it's a first, second order reaction, and we divide it with this relationship between the dispersion and the linear velocity, and finally we take the conversion into account. And yeah, the Bodenstein number is basically the Peclet number, but using the particle diameter as the characteristic dimension. And it comes out looking something like this. So if you have a gas phase reaction, if you have 2 millimeter particles, you have to have something like 10 centimeter long bed for 80% conversion, going up towards 100 centimeters, maybe 50. This is a logarithmic scale, and you should do your own calculations. And red is second order reaction. So if you have second order reactions, the effect of the dispersion will be higher. Blue here is first order reaction. And you can see that there's a dramatic effect when we go down in particle size. So if we have 0.1 millimeter particles, we have less than 1 centimeter to a few centimeter in bed length. In the liquid case, it's roughly a factor of 10 larger. So from 100 to 5,000 centimeters, and then yeah, with smaller particles you have from 10 to maybe 50 centimeters in this case. So make sure that you can avoid concentration gradients in the axial direction, and basically what we're checking for here is how close to a plug flow reactor we actually are. So if you have a low relationship between the actual dispersion and the linear velocity, you will have more tank reactor behavior than a plug flow or ideal plug flow reactor. And that's what we're checking for here. Then we also need to determine the minimum reactor diameter. And this is for gas phases. In the gas phase, we need to make sure that the packing of the catalyst, which we do in the reactor, well, it should be representative. So when you have a solid wall that isn't packing, you will get a less dense or less closely packed catalyst bed around the circumference of the reactor. And to be able to neglect this, we want to neglect this, otherwise we'll have too high, well, you will have some kind of bypass. It's not really a bypass, but there will be an overrepresentative amount of the flow passing through this lightly packed layer of catalyst, and it will skew your reaction. It will produce less contact with this catalyst here, and you will underestimate your activity and selectivity, well, activity at least. And the criterion for determining this minimum reactor diameter is actually quite straightforward. The only thing you need to do is take your reactor tube or the diameter of your reactor tube and divide it with your particle diameter, and make sure that it's more than 10 particle diameters on the reactor tube diameter. If you're there, you're pretty good with respect to packing. There are some other criterion out there that say 8 to the radius or 16, but somewhere between 10 and 15 will give you a good reason to ignore these wall effects. For liquid solid reactions, it's actually the other way around. There you have a maximum reactor diameter that you need to consider. So for gaseous phase reactions, it's a minimum reactor diameter, and for liquid solid reactions, it's the maximum reactor diameter. Here we are looking at the radial diffusivity. Yeah, so how much the again, so how much the molecules in the liquid are moving compared to the radial direction compared to the length of the bed, and we then divide this again with the linear velocity, the reaction volume, the packing factor divided by kappa, and kappa here is sort of a dimensionless number related to the flow profile. And yeah, you probably need to go to the actual paper because the explanation is a little long to do in this forum here. But basically, it comes down to comparing the diffusivity in the radial direction to the space velocity. So how much flow you have compared to the catalyst volume. You have the reaction order in there, and again, you have conversion in there. So the take-home message, make sure that you have a large enough reactor diameter for doing gas phase testing, and make sure you have a small enough reactor diameter for liquid flow testing. Then finally, what we need to do is determine the actual pressure drop in the catalyst bed. Here we're using Ergun's equation. So we have this equation here which relates the pressure drop of the bed to the length of the bed. We have two parts to this equation, one which represents the laminar flow and one for the turbulent flow. And we have factor multiplied with the dynamic viscosity. We divide it by the particle diameter, and then we have a relationship between the packing of the catalyst bed. So this is basically the difference between what is material and what is void in your bed. And then you have the linear velocity of the bed again. And linear velocities in through and through should always be calculated without anything inside the catalyst bed. So it's empty flow rate. For the turbulent part, again, we have a factor. It's multiplied with the density of the gas, particle of the diameter. Then you have a different relationship between the packing and void in the bed. And then finally, you have the linear velocity squared here. And if it looks empirical, it's because it's empirically derived. So this is experimentally determined, and it works rather well, though. You will most likely not have round particles, so then you have to make some estimate or use a factor for, well, to compensate for your shape of the particles. Then what we want to make sure is that the pressure drop over the bed is less than 20% of the total pressure. So if you have a higher pressure drop than 20%, it's not fair to say that your testing is isobaric. And yes, then you have different contact times in different parts of the reactor for gas flow. And yeah, that's going to mislead your testing. Final thing in the reactor is to determine if we have a temperature gradient in the radial direction. So here we want to be able to neglect the temperature differences inside the reactor going from the center of the tube to the wall of the tube. And we are again working with the these dimensionless numbers. In this case, it's the bio number. The bio number is the relationship between the conductivity of the bed. So this is basically how well heat is transported through the bed. And this is how the lambda is how well we can conduct or transfer that heat through the wall and out. And this determines how well heat is transported through the system. Then we put it into the other equation up here, where we again have a term here, which is the transport of the heat from the out of the reactor. So this is the conductivity through the bed, and this is the wall temperature. So this is how much driving force we have for moving heat out of the reactor. And up here we have the production of heat, and this is the reaction heater reaction, how much kilojoules per mole is produced. The R here is of course the reaction rate, so these two multiplied with each other will tell us how much heat is produced. This is the packing factor again, so it's only relevant to take into account the actual catalyst volume here. And again, the second factor here also does that, because B is how much you actually dilute your catalyst. So this is the dilution factor. If you're not testing with 100% catalyst, you dilute it with something else, you also have to compensate for that. And then this is the radius of the tube. You also need the activation energy, Arrhenius correlation, and you relate it to the particle and tube diameters here. And we have to make sure that this expression here is less than 5%. And if it's less than 5%, we can be quite comfortable with neglecting the gradients in this direction as well. Okay, so now we move to the actual particle. So now we tried and we investigated how does the gradients look inside the reactor. Now let's look around the particles, the catalyst particles, and also inside the catalyst particles. So if we look at the catalyst cycle, we have not only the reaction, we also have transport phenomena. And the first thing that we need to do is move a reactant from this gas bulk that is flowing around the catalyst particle into the catalyst pore system. And to do that, it has to pass through this layer where the gas isn't moving. We call it a stagnant boundary layer. So around the particle, you'll have a boundary layer where you have very little or actually no movement of the gas, and then in that region we're relying on this diffusion of the molecule. So it has to diffuse from the gas bulk through this stagnant layer, but it doesn't stop there because the reaction doesn't occur always here. You also have to consider the diffusion that is inside the catalyst pore. So it has to diffuse, it has to adsorb to the catalyst surface. There we have the intrinsic kinetic, the reaction rate going from 4 to 5, from red to green, green being a product. Then it has to desorb. Then the product has to do the same journey back, so diffusing through the pore system and diffusing through the stagnant layer to go out of the reactor. And this can create problems because you have a certain concentration in the bulk. So we have an inlet concentration. The concentration will change, but we have concentration gradient. So over the particle boundary layer, there will be a lower concentration at the radius of the catalyst particle than in the start of this stagnant boundary layer, and that's also the driving force for the diffusion. If there was the same concentration, there would not be any transport of material. Well, there will be, but the same concentration would be the same. And then you will have, in this case, further concentration gradient moving from the side of the catalyst to the center. So moving into the catalyst particle, you will have a consumption of product, so you will actually see a lower concentration inside the catalyst particle than on the outside. And if this is a reaction that produces heat, you will actually see a much higher temperature in the center of the catalyst than in the bulk. So getting heat production in the center of the catalyst and not being able to transport it fast enough out to the temperature will create a gradient. And we need to make sure that this is a known gradient and that it's a under control, or so to speak. And the same thing goes for endothermic systems with the concentration profile, but then the temperature will of course be lower in the center than outside, since it's consuming heat. So let's start looking at these outer mass transfer limitations. This is a rather simple relationship. So we have to look at what happens at the surface. So this is our observed reaction rate. This is how fast we are consuming reactant A in the system. So this is how often we, or how fast we lower the concentration of A. Then this is how fast we can actually move reactant A to the surface. And I'm sorry if I'm confusing you a little, because A here is not the reactant. A here, or A prim, is the relationship between the surface area of the particle and the volume of the particle. So it's the square meters of the outer shape of the particle divided by the volume of the particle. And the reason for having this relationship is, of course, because we have the entire catalyst volume being active for the reaction, but only the surface area, the outer part of the catalyst, being related to the transport of material to the catalyst. Kf is our mass transfer coefficient, and this is the concentration in the bulk, which is our driving force for moving molecules. So basically, how fast do we convert molecules inside the catalyst, and how fast can we move it there? If we move it almost as fast as we consume it, so if it's the difference is less than 5% divided by the reaction rate, we can say that it's negligible. Then we do the same thing again. We connect the reaction rate to the heat produced. So this is the heat produced. So this is the heat of reaction. Again, the mass transfer factor, how fast we're moving things to the surface, and this is the concentration. So this here is the heat produced in the system, and this is the heat transfer out of the system. So where H is the gas solid heat transfer coefficient, and T is, of course, the bulk temperature. So this is heat produced, this is heat transported out of the system. And if that is less than 5%, again, we can neglect temperature gradients. Finally, we look at what happens inside the catalyst particle. So the catalyst particle is also porous on the inside. It has voids inside the particle where we can have a lot of reaction. And here we'll have to look at how well we can transfer molecules from the surface after molecules diffuse through this stagnant boundary layer. How fast can they move into the catalyst particle? And again, we use the observed reaction rate, and we use the characteristic catalyst dimension. So this is a meter or some geometric shape of the particle. So this is basically the consumption of material or consumption of product, consumption of reactant, I should say, production of product. And we relate it to how fast we move things inside the pores. So this is the effective diffusivity, which is of course then influenced by the temperature. It's influenced by the type of molecules that are diffusing, but also the pore system. So the smaller the pores, the lower the effective diffusivity in general. And we have here the driving force, which is the concentration on the surface. So after diffusing through the stagnant boundary layer, this is the diffusion at the surface, so the concentration at the surface. Multiplying it with some version of the reaction order, so 1, 2, 3, whatever we have, and in this case it has to be less than 15% to be negligible. And finally, what we can do is the same thing as we did before. Take a look at, okay, how much heat are we producing? It's this term here. The observed reaction rate multiplied by the heteroreaction, the effective diffusivity, and the surface concentration. And then we look at how fast we can move that out, which is basically heat transfer through the particle to the catalyst surface. So if the heat produced versus the heat transfer is less than 10%, it can again be neglected. And then you can dive a little deeper into this. This term here can actually be called also the Wheeler-White's module, sort of a function of the effectiveness factor times Thiele's modulus. And this other part can be abbreviated beta. It's sort of the inner temperature gradient calculation. And we can use this to show what happens if you don't treat your gradients in a good way. And basically what this tells us is if you have unfavorable conditions, very strongly exothermic, and you have a very large gradient in your particle, you can actually overestimate your reaction rate rather significantly, which means that when you go to scale up, you will overestimate the number or underestimate the amount of catalyst you need, and therefore you will build a too small a reactor. On the other hand, doing the same thing for endothermic reactions is of course safer because you only risk overestimating your reactor size, but to be honest, it might mean that you wouldn't build a reactor. So how do we handle gradients? Well, one way to do it is to dilute. So by dilution, you can reduce the amount of heat produced. You can improve the, also you don't reduce the amount of heat produced, but you reduce the amount of heat produced per volume. So per cubic meter of reactor, it's much less, or per cubic milli, or per milliliter in this case, might be a better measure. So you spread the impact of the reaction heat over a larger volume. You also decrease the effect of axial dispersion because you have this higher bed, but you need to make sure that you don't get too high pressure drop. And another thing that you have to make sure is that your material is inert so that it doesn't influence the reaction. We use typically low surface area materials, and in our case it's usually silicon carbide because it's also a great heat conductive material, but quartz, alpha alumina, and glass can basically do the same job. But we need to make sure that it doesn't affect conversion, and you do that by applying this relationship. So you take 2.5 times the dilution factor, multiply it by the particle diameter, then you divide it with the 1 minus, so this is the catalyst part, and this is the length of the bed. And if it's less than 5%, again, you can neglect the dilution. All right, so these criteria are great. It gives you a good indication, but there are some difficulties, of course. These parameters that we need, like heat conductivity in the bed, effective diffusivities, mass transfer coefficients, they can be difficult to come or come by. And also, in some cases, we need an absurd reaction rate, and that means that we need to start doing the experiments before we actually know if the experiments are correctly performed. So some of these are difficult to estimate, so therefore it's always recommended to do verification experiments. And this can be done for many different criteria, but let's start at looking at the internal gradients and also the external gradients. So internal gradients you can check by changing the particle diameter. So if you have limitations to heat and mass transfer inside the particles, making the particles smaller will show this. Also, if you have a problem moving things like heat or material from the bulk to the surface, increasing the linear flow rate in the reactor will show this. So basically you can do this diagnostics test like this. So if you have a flow rate going through the catalyst, you have a certain conversion, you have large or small particles in this case here, and you make the catalyst particles larger and larger and larger, and you get different conversions. And if you start from the end of large particle diameter and you, for instance, make the particle diameter half of what you had and your conversion increased, then you know that you had a gradient. So then you do it again, you take half of your diameter and you get an increase again. You still know that, okay, then we still have a gradient. But if you take your catalyst particle and you crush it and sieve it to half the size and you get the same conversion, then you know that we are in a regime where we do not have influence from inner particle transfer of heat or mass. And the same thing goes for the outer gradients. You can have a constant relationship between the flow rate and the catalyst. So you start with a small flow rate and a small amount of catalyst, and you get a certain conversion. Then you increase the flow rate, you double the flow, but you also double the catalyst volume, which means that you're operating effectively at the same space velocity, but you're increasing the linear flow rate through the reactor, which means that you are effectively shrinking the boundary layer around the particles. And if you do this for several flow to catalyst volume ratios, you can get the same type of plot. But here we have at a low flow rate, we get a certain conversion, increasing the flow rate and the catalyst volume. So the same relationship still gives you a higher conversion. Then you know that you had a gradient. And again, doing this repeatedly until you do not see an increase in the conversion gives you an easy diagnostic test to prove that you're actually working without a gradient or outer gradient in this case. So some general advice. So if you have temperature gradient or you suspect it, dilute it with an inert heat conducting material. Again, if you do see a change in conversion, then you had a gradient. So you can do the same thing. You can test with one dilution ratio, get a conversion, increase the dilution ratio. If you get the same conversion, then you know that you weren't operating with gradients. Finally, if you are calculating an activation energy, you can actually use that to assess the gradients. And that is basically done by increasing the temperature. So you have you calculate your activation energy for this regime, and if it's the intrinsic surface reaction where the reaction on the surface is controlled, it's not influenced by any heat or mass transfer, you will get the actual chemical reaction, and it's the heterogeneous activation energy depends, or the slope depends on that. If you increase temperature, at some point you will start to see limitations in transporting things from the radial or the outer shell of the catalyst into the center, and you start seeing pore diffusion limitations, and you get a different slope. So this slope is about half of the non-pore diffusion control one. And finally, if you continue to increase the temperature, you will actually produce a constant, because here it's independent of the reaction. It's just a fixed value. It's how fast you're transferring things from the bulk to the surface of the catalyst, which is the same for any catalyst. And then you get a fixed value, something between 4 to 12 divided by R. It depends on the size of the molecules, etc. And of course, you can go into final regime. If you continue to heat, you will actually start to see a homogeneous phase reaction, but that's not something we consider here. So to conclude, we have several reactor types available. We make these choices depending on the reactor, depending on the application. If it's a screening, if it's verification, if it's diagnostics, we choose reactors differently. In the testing, we keep track of the gradients, especially when we do screening and activity measurements for new reactions. And we try to avoid these gradients, and we do that by a combination of experiments and calculations. So you go through these criteria perfect, but also do these diagnostics tests to verify that you have a small enough particle to avoid inner mass and heat transfer, high enough linear velocity to avoid gradients between the bulk and the catalyst particle, and that you have enough dilution of your catalyst to avoid reactor temperature gradients. All right, so that was about it. I have included some slides here with further reading, so you can go through that if you're interested. This presentation is, of course, just a summary of much of this. And so go through this literature, and I'm sure you will have a lot of fun. And then finally, we have the nomenclature, and this is just the nominations that were used in the equations. As always, if you look in the client, you can actually download these slides, or they will also be sent to you in an email later on. And with that, I would like to thank you very much for your attention.